All right, good evening and welcome to lecture number 18 for MT225. So the last few weeks we've been working on structural analysis. We've been looking at truss problems and solving trusses, finding unknown loads carried by members given the geometry of the truss. Tonight we're going to go a little bit beyond the truss into a new structure that we call the frame. In the frame, we relax some of the constraints that we had that made a truss a little simpler to analyze. Now, that means we end up being able to say less about the individual members that make up a truss or that make up a frame, but that we can handle slightly more or slightly different geometries. So we'll see how that works. It's actually not that bad of a problem compared to dealing with trusses. It's very rare to involve a sine or a cosine, for example, in any of these problems. We can work them out for the most part algebraically without any kind of trig coming in. So a little bit more complex on one side, but a little bit simpler algebraically and mathematically. So it kind of balances out. So let's see here. So homework 7 is due on Wednesday. Homework 7 is our homework on the method of sections, and I'll be asking if there are any questions on that here in a moment. Quiz number 5 has been posted up on the website. That was posted yesterday. I think I got it in the morning yesterday, so it's been up there for quite a while. Due tonight, and that is one method of joints problem. Quiz 5 is on homework number 6, which was method of joints. So similar to that homework assignment. And exam 2, looks like we are pretty rapidly heading toward exam 2. In fact, we should be in a pretty good position for that next Wednesday. So next Wednesday will be exam 2. It's only covering trusses and frames. So it's basically covering the last roughly 2.5 weeks or so of content. So we'll have problems on method of joints, problems on method of sections, and frame problems. We'll be finishing up with frames this week. Monday night next week will just be a problem session on working out problems in truss analysis and frame analysis. So we'll be practicing any of the types of problems that could show up on the exam. And I have posted a sample exam too. Not quite last year's exam, but one of the previous ones. It's pretty representative of the kinds of problems that show up on exam number 2. And reminder with respect to exam 2, we're doing those in person, unless some other arrangements have been made. And that's at 5 p.m. at the hangar. Pizza will be provided, so be aware of that. And you are allowed to have 2 reference cards, 2 4-inch by 6-inch cards that you can put anything you want on. So that's an option for you to take advantage of. All right. So any questions on the homework? All right. Well, I'll remind you that on Wednesday night, just like I did this previous Wednesday, any particular question that's on there, we can, as a class, or at least of those in synchronous attendance, can ask to have one of those problems worked out. And there's usually a candidate problem for that. I think that roof truss problem is going to be one that people have questions on, but it's also pretty similar to one of the practicum session problems that I did last Wednesday night. So you might want to check that one out on video if you haven't seen that already. All right, so let's take a look at frames. Now, one of the assumptions we made with trusses was that we had what we called 2-force members. A 2-force member has a force that is only along the line of that member. And that meant that we could only put forces at joints in the trusses. We couldn't load up a member in the middle or in between 2 joints or someplace off, some distance away from one of the joints. Frames allow us to relax that. Frames allow us to load the structure anywhere, including in the middle or somewhere in between one joint and another. And that sort of breaks the two force nature. And I'll show you that in a second here. So in a frame, we have a generalization of a truss. It's a little more general, a little closer to reality, has fewer constraints on it than the regular trusses have. And they allow multiple force members. So let me go over to the page here, and we'll take a look at what the multiple force member is compared to the two force member. So if this is a truss member, let's just say it's over here somewhere. So this is just one member in the truss. There's a joint at one end, a joint at the other, and we saw that the forces on that member had to be aligned with the member itself. So the force, whether we're doing method of joints or method of sections, if we're doing method of joints, we might have something that looks like that. If we were to cut through here, we'd expect our free body diagram to have something that looks sort of like that in it. So the force direction was automatically determined by the direction of the member. In a frame, that's no longer required. We could have, for example, in a frame, we could have, well, let's just take a simple 3-member kind of structure here. We might have pins at each of those joints, but if we put a weight right here in the middle of this beam where there isn't a joint, well, now the forces at the end, we know what those reaction forces would look like. Those reaction forces would be up like this. That's not along the line of the member. When you add in what's going on with the sides here and any other forces that might be on the system, the reactions at the joints at the end of the members might be off in some direction, different than the direction of the member itself. So we can no longer say that the force that the joint experiences due to a particular member is along the direction of the member itself. It might be in some other direction, depending on how much load is placed where. So it can become much more complex. And if we were really interested in figuring out the actual loading of this member, we wouldn't really be able to describe it, because it's no longer just tension or just compression. When we loaded up a truss, if the forces are only at the ends, only at the joints, then each member is either in tension or in compression if it's got a load on it. Well, a member like this isn't in tension or compression, it's in bending. If we were to apply this load, if this was a very heavy load, we'd expect the member to kind of do that, to kind of bend. And bending is a combination of tension and compression, where you've got tension on one side and compression on another. So in frames, we allow for bending to be a possibility, and that makes life all sorts of complex if we really want to figure out what's going on in the members. Fortunately for us, the question that we ask about frames in this class is a little simpler. All we're interested in figuring out is what's going on at the joints. We're no longer going to be able to ask the question, is this member in tension or is it in compression? But we can ask how much force in total is on these members, on these joints, and are they going to shear through? If we had, for example, a material that joint was made out of, we could look at the total force on that joint and ask, is this going to break? That's about the limit of what we can really do in this particular class. So in a frame, we're interested in figuring out what's going on at the joints. How much force does that joint feel in the X direction? How much force does that joint feel in the Y direction? And then what the total force is. Remember that when we have components of a force, if we have an X component and a Y component, we can find the magnitude of that force by using the Pythagorean theorem. So the final step in a lot of these frame problems is to use the Pythagorean theorem to figure out the magnitude of the force acting at each joint. That's what we're after in our version of frame problems. So let's see how we can set one up. So in a frame, we have multiple force members, which means that they could be in tension, they could be in compression, they could be in some mix of the two. Bending. In a three-dimensional problem, we could have what we call torsion or twisting. So we can't really tell what's going on in the individual members. It's too complex. Instead, we focus on the joints. And in the joints, we look at the maximum load that's exerted on that joint. So we can load up the members anywhere we want, not just at the joints, but we're only interested in calculating the forces at the joints. So frames are held together with pins, the same exact pins we use to put trusses together. The difference here is how they're loaded, that they are loaded in more complex ways, in more directions than we might have with regular trusses where we only have two force members. So to analyze a frame, we still use the technique of using free body diagrams. We want to find the unknown reactions at the pins. So in a sense, this is kind of like going back to a beam on a set of supports kind of problem. So for example, here, if we have a beam sitting on a pinned support, we knew that we could draw a free body diagram of that by replacing that pinned support with two forces. The two forces supplied by that pin. A roller only supplies one force perpendicular to the surface that it's on. Well, whether that pin is shown as a triangle, a hinge, or whether it's shown as just a point, it still contributes two unknown forces. There's a force in the x direction and there's a force in the y direction. So each pin gives us two unknowns. And if we have a free body diagram that's non-concurrent, we can handle up to three unknowns because we have three equations: the sum of forces in the x direction, sum of forces in the y direction, and sum of moments about a point. So we're going to use that. There's one little quirk in how we draw out our free body diagrams that I'll have to go over, but you'll find some of this to be pretty familiar. If you're comfortable with finding reaction forces at supports, you're going to see a lot of familiarity with what we're doing here. So let's take a look at it. So in a frame, our goal is to find the unknown reaction at the pins. So each pin has two unknown forces, an x direction and a y direction force. Once we find out what those are, we'll use the Pythagorean theorem to find the magnitude, since x squared plus y squared, square root, gives us our magnitude. So it's pretty similar in sequence anyway, to what we're going to do to analyze a truss. It is a little bit different though, because we're going to see some things that we haven't seen in working with trusses. And here's a good example right here. So this is something that is a nice simple frame. It's a two-member frame. There's a vertical member and a horizontal member, and there are two pinned supports. Also not quite shown directly in this drawing, but it has to be there, is a pinned support at B. Anytime members are joined together, there's got to be a pin where those members are joined together. So we're going to have forces on this pin at A, we're going to have forces on this pin at C, and we're going to have forces on this pin at B. Each one of those represents two unknowns. So in total, we have 6 unknown quantities. Well, we've seen that we can handle 3 unknown quantities. When we did method of sections, we had to make sure our cut through the truss only went through 3 unknown members, because our setup and our equations of equilibrium could only handle 3 unknowns. That we have 6 unknowns here means that we're going to have some issues with our equations. Whenever you have more unknowns than you have equations, what it tells us is that we're not going to be able to solve the equations right away. We're going to be able to come up with relationships between our unknown quantities. We'll have equations that our unknowns must be able to solve, I must be able to satisfy. But we might not have all the information out of one free body diagram to get everything that we want. Generally, if you can count up how many unknowns you've got, that'll tell you about how many free body diagrams you're going to have to work with. In this problem, we have a total of 6 unknowns. 2 unknowns at A, the X and Y direction reactions at A, 2 unknowns at C, the X and Y direction reactions at C, and 2 unknowns at B, those X and Y reactions. Well, each free body diagram gets us 3 unknowns. So if I've got 6 that I've got to find in total, I'm going to have to do 2 free body diagrams. And any 2 free body diagrams will do. One would be to use the external problem. The same kind of external problem we solved on trusses. We can look at what the supports are, the reactions are at A and C, and treat B as an internal force. And that won't show up in our equations. So let's start there. Let's draw the free body diagram of this structure and solve the external problem. So in copying this over, I'm going to label the top member AB and the vertical member BC. So we've got B, C, A. Point D is just telling us where that 200 Newton force is. So I'm going to leave that symbol out. I'm going to leave the letter D out, but that is right in the middle of this 4 meter long beam. So that's 200 Newtons. And then we've got 5 meters from B to C, 1 meter up from B to the end of the beam, and that happens to be where we've got 500 newtons of horizontal force. So let's take a look at that on the page here. There we are. So there's our part of our diagram where I've left off that this, we'll draw it down here. We've got 2 meters here and here. Now at A, in our original drawing, we have a pin. We have a pinned support. And a pinned support contributes 2 unknown forces. And we'll call them RAX and RAY. Just like we have for about a dozen problems so far. At C, we also happen to have a pinned support. That's the weird part here. That's a little bit different. In all of the beam problems and even all the truss problems that we solved, we had 1 pin and 1 roller. That guaranteed that the external problem only had 3 unknowns because a roller only has 1 force. And so we'd always get numbers for our values for our reaction forces. But because of the constraints that have been relaxed with a frame, we no longer have to have only 3 unknowns in our external problem. We could have 2 pinned supports here, and we do. So we have reactions here at joint C, and we don't know what those are. We'll call them RCX and RCY. Now, what we want to build as we are analyzing this frame is a table with 3 columns in it and as many rows as we need for the number of joints that we've got. And we've got 3 joints here. We've got joint A, joint C, and joint B. So we'll label those A, B, and C. That'll be our joint or our pin. We're going to want the X force and the Y force on each of those. And in this problem, those are in newtons. And then we're going to want our magnitude also in newtons. And remember that the magnitude is going to be the square root of the force in the X direction squared and the force in the Y direction squared, the sum of those 2 squared. That way we're getting the magnitude of the force. So we combine our X and Y components at each joint. We usually do that at the end. So we'll fill out the table here, and here we can pretty clearly see our 6 unknowns. They're right here. 1, 2, 3, 4, 5, 6. 2 unknowns for each pin. So let's work our free body diagram. This is a non-concurrent force system, so we have 3 equations of equilibrium. We can have our sum of forces in the x direction. We have our sum of forces in the y direction and sum of moments about a point. So let's do our sum of forces in the x direction. We've got RAX positive, since our coordinate system would look something like this. So we've got our sum of forces in the x direction. We've got RAX to the right, so that's positive. We've got this 500 Newton force to the right, so that's also positive. And then we've got RCX, which is also to the right. So that's positive. No other forces that I can see in the x direction, so that sum will be equal to 0. We can take our sum of forces in the y direction. In the y direction, we have RAY positive. We have a minus 200 newtons. And then we have RCY positive. No other forces in the y direction, so that's our y direction sum. And then we need our moments about a point. And this is where we have to be really careful. Moments can be tricky already in a truss problem because horizontal and vertical moments can come into play. In trusses, we always found that we could pick a pivot point that would give us an equation we could solve, that would give us an equation with only one unknown. That's not always going to be true with frames. When we do when we figure out the equations of equilibrium for a frame, there may not be a point we can pick to guarantee us only one unknown. We also have to be careful because there are going to be lots of forces that cause moments depending on what we pick. So you got to make sure you catch all of them. If you miss even one of the unknown or one of the moments in the problem, it'll throw everything off. So let's see what we've got here. We've got 3 possible pins to use or pivot points to use. We could use A, and that would knock out RAX and RAY, but the 200 Newton force would have a moment, the 500 Newton force would have a moment, and both RCX and RCY would have moments. If we picked B, well, RAX wouldn't have a moment, but RAY would. So would the 200 Newton, so would the 500 Newton. RCX would, but RCY wouldn't, since its line of action goes through B. So we lose 2 of our unknowns, but we still have 2 others in, just like we had at A. And C, we've got the same problem. If we pick joint C as our pivot point, we'll lose RCX and RCY, but 500 newtons will still have a moment, 200 newtons will still have a moment, and both RAX and RAY will still have moments. So there's no way around it in this problem. No matter what point we pick, we're going to end up with an equation that has more than one unknown. So let's go ahead and do that. I'm just going to arbitrarily pick A, since that's what we've picked in most situations. So RAX and RAY, no moments there, but everything else will have a moment. And one of the most common errors I see across all of these problems, even the external problem on trusses, is people missing moments. So take some care here, step through, make sure you've got all the forces that create moments, and each one of those produces a term in your sum. Here I've got 4 check marks, 4 forces that will create moments, so I better have 4 terms in my moment equation. So let's do our sum of moments about a point. So we'll do sum of moments about A. Well, at A, I have this 200 Newton force 2 meters away. So that's 2 times 200, that's 400 Newton meters. pinned at A, pushing down clockwise, and clockwise moments are negative. So there's one term. The 500 Newton force has a moment. Remember, to figure out the arm, you'd have to project the line of action down and see how close that line of action gets to A. The perpendicular distance between the pivot point and the line of action here is the length of the distance between B and the 500 Newton force, and that was 1 meter according to our drawing. So the 500 newtons is at 1 meter. So that's 500 Newton meters. If we pin at A and we pull to the right there, that would be a clockwise moment. Clockwise moments are negative. So we have negative 500. Then we have RCX. RCX is 5 meters away from A. Essentially, if we bring the line of action down through like that, this distance, A to RCX's line of action, is 5 meters. So we have 5 RCX. If we pin here and we pull to the right there, that would be a counterclockwise moment. And counterclockwise moments are positive. So we have plus 5 RCX. Then we've got RCY. RCY's line of action's right here. That's 4 meters away from A. So we have 4 RCY. If we pin at A and we push up at C, that would again be a counterclockwise moment. And counterclockwise moments are positive. So 4 terms in our moment equation, 4 forces causing moments. Well, let's clean up these equations a little bit here. If we look back at them, the x direction equation we can't solve right now because we have too many unknowns. RAX and RCX, we don't know what those are. Y equation, we're in the same boat. We have 2 unknowns, so we can't solve that. And the moment equation, we've got 2 unknowns. We've got RCX and RCY. We can't solve any of these three equations. This is the worst case scenario for an external problem. We get 3 equations, but no numbers. We got no answers. But we have gotten some information. What these equations tell us are constraints, relationships between these unknown quantities that must be true. For example, here in my x direction equation, if I subtract 500 from both sides, it says that whenever I take RAX and I add it to RCX, I need to get a negative 500. That's a relationship between RCX and RAX that keeps RAX and RCX from being anything. They could be otherwise any values. Here they're constrained, they're related to each other. Whatever RAX is, we have to add RCX to it and get negative 500. We can do the same thing with RAY and RCY. RAY and RCY can't be just any numbers. They have to be numbers that when you add them together, you get 200. If I add 200 to both sides, I'd get RAY plus RCY equals 200. And in our moment equation, we can combine these two together. That's negative 900. But if we add 900 to both sides and clean the equation up a little bit, we get 5 RCX plus 4 RCY equals 900. That's another constraint. That says that RCX and RCY can't just be any old 2 numbers. They have to be so that when you multiply RCX by 5 and add it to 4 times RCY, they have to add up to 900. So while we haven't gotten any numbers, we have gotten 3 equations that our answers have to satisfy. So that's at least something. And we might not be able to use these equations right now, but we can use them later on. If we get some more information, we can go back and reference to them. So while we might not be able to use it right now, we can store them for later use. So what I usually do is write them up next to the table that I'm trying to fill in as information that might be useful later, but that I haven't got enough information to use right now. So we've got RAX plus RCX is negative 500. We've got RAY plus RCY equals 200. And we've got 5 RCX plus 4 RCY equals 900. And we're kind of stuck here because we don't even have simultaneous equations. We could try doing various substitutions and things like that, and we might get lucky and be able to eliminate something. But chances are, with 6 unknowns, all you're going to do is end up with 6 different combinations of those 6 unknowns. Being able to eliminate one of them, you might get, for example, you could replace RCY here with RAY and some numbers, but then you've got an equation in RCX and RAY instead of RCY. So it usually doesn't end up helping. There are simpler ways to get the information we need. So at this first stage of the problem, where we've done the external problem, we're kind of out of luck. We haven't been able to really solve anything. We need to get information from someplace else. And the critical idea that helps us get the information we need is to use the same idea that we used with method of joints and method of sections. The critical idea that makes method of joints and method of sections work is that if a whole structure is in equilibrium, then every piece of that structure is also in equilibrium. So when we have a structure, every piece that makes up that structure must also be in equilibrium. That means that the members here must also be in equilibrium. So if we consider the free body diagram of just member AB or the free body diagram of just member BC, we might be able to introduce some information that would help us unravel this tangled mess of these equations. So let's draw the free body diagram of member AB. So we've already got part of it. We've got the member itself. At A, we've got RAX and RAY. And it's important to make sure that you use the same directions for the arrows in the free body diagram. If you've already made assumptions about those arrows for a joint like A here, keep the directions the same, because these equations over here were built based on these assumptions and those directions. If you change them, you'll get values that have a different set of assumptions associated with them. Now, there are some times where we do have to change directions, but that never applies to the external supports. It's only the internal joints where we might have to do that. And I'll show you that in another example. Now, joint B is also a joint. It's also a pin. So it's got 2 forces associated with it. If I get rid of member BC, I've got to replace it with the forces that member BC supplied. So I always make sure when I'm picking a new member or a new joint that I haven't worked with before, when I'm exploding the truss into its individual members or the frame into its individual members, I always assume positive. So I always assume RBX and RBY. I always assume those to be in positive directions for reasons that will become clear in the next problem, in the next sample. This one's kind of simple, doesn't really give us the problems that can possibly come up. But for reasons that I'll explain later, it's always safest to assume positive directions the first time you draw the free body diagram involving a joint. Now, I've got that 200 newtons in the middle. So there's our free body diagram for member AB. Well, we can come up with our equations of equilibrium for that once we have our coordinate system defined. We have our sum of forces in the x direction. We have a positive RAX and a positive RBX. Nothing else there. No other forces in the x direction, so that sum is equal to 0. We can take our sum of forces in the y direction. We've got a positive RAY and a positive RCY, BY, excuse me. We've also got a negative 200 newtons. And that equals 0. So far, it's not looking a lot greater than what we've already done with the first set of equations from the external problem. But moment's going to help us out quite a bit here. Let's take A as our pivot point and see what happens with the moment. If we take our sum of moments about A, well, let's first count up the forces that'll have moments. RAX and RAY, no moment there because they push on the pivot point. The 200 Newton force, definitely, it's going to have a moment. It's got an arm. RBX, the line of action of RBX shoots right through A. This is a horizontal member. So no moment there. RBY, yeah, it's definitely going to have a moment. There's only one unknown force in those two. So that means our equation of equilibrium we're going to be able to solve. We'll finally get a number that we can fill into our table. So let's see how it works. RBY is 4 meters away. So we have 4 RBY. And that would be a counterclockwise moment, so it's positive. The 200 meters is 2 meters away, so that's 400, 2 times 200, 400 Newton meters clockwise, so it's negative. Those are our two terms for our moment equation. And to be in equilibrium, the sum of moments has to be equal to 0. Well, we can solve that. If we add 400 to both sides, we have 4 RBY equals 400. Divide both sides by 4, and RBY is 100, and the units are newtons. So finally, something we can fill into our table. Right here, the y direction force for member B, or for joint B, is 100 newtons. All right, one unknown down out of 6. Well, let's see if we can solve anything else from that. Well, if we know RBY, we can go back into our y direction equation. RBY is 100. So we have RAY plus 100 minus 100. That's RAY minus 100 equals 0. If we add 100 to both sides, now we've got RAY equals 100 newtons. So we've got another number we can plug into our table. We've got our y direction force, RAY. So that's 100 newtons. And then we come to our x direction equation. Well, x direction equation, we're kind of stuck there. We don't have enough information. And we could have predicted that too because we had 4 unknowns. 4 unknowns with 3 equations, we're not going to get all numbers. But this is kind of the best case scenario for having 4 equations and 3 unknowns. We got 2 numbers and 1 equation. The worst case scenario is we get 3 equations we can't solve. That's basically what we got in the first setup. But in our second equilibrium problem, we were able to get 2 numbers and 1 more equation. So we can't use that equation just yet. So we'll go up into our equation bank here and store it. RAX plus RBX equals 0. That means that whatever RAX and RBX are, they got to be opposite signs and they've got to add to 0. Well, with the information we've got now, let's go back to the table and see if we can solve anything. We got 2 new pieces of information here. We know RAY and we know RBY. Well, we can go to any of the equations here that involve RAY and try and solve them now. The only equation that involves RAY is this one right here. RAY plus RCY equals 200. Well, RAY is 100. What would we have to add to 100 to get 200? Well, 100. So RCY must be 100. So there's another unknown down. Now that we know what RCY is, we can go to other equations that involve RCY and try and solve those. Our moment equation from the first setup involved RCY. So we can go down to some scrap area here. There's our RCY equation. We know RCY is 100 now, so we can go and work with this. We got 4RCX, 5RCX plus 4 times 100 is 900. So that's 5RCX plus 400 equals 900. Subtract 400 from both sides, and 5RCX equals 500. Divide both sides by 5, and RCX equals 100. So there's another number we can plug in. RCX is 100. And we've used this equation. So we can kind of cross out the equations we've used in our equation bank. We're not going to be able to use those again. So we were able to use those two. Well, let's see if we can work with any of the others now. Well, RAX plus RCX is negative 500. We know what RCX is now, so we can figure that out. And RAX plus RBX, well, we don't have enough for that yet. We don't have either of those two. So it looks like we've got to go to RAX plus RCX equals negative 500. RCX is positive 100. And if we subtract that 100 from both sides, RAX is a negative 600. So RAX is a negative 600. Now we can finally go to our last equation, our last remaining equation, RAX plus RBX equals 0. Well, RAX is negative 600 plus RBX equals 0. Well, the only thing we can add to negative 600 and get 0 is positive 600. So RBX is a positive 600. So it wasn't looking too good at first. We did one setup and we got 3 equations and no numbers. But then we realized that both of these members must be in equilibrium. So by drawing the free body diagram of one member or the other, we could do sum of forces and sum of moments and potentially get some information. That got us 2 numbers. But with those 2 numbers, we were able to solve other equations and everything unraveled. Sort of like if you're a fan of playing various games like Sudoku and things like that, you get one critical piece of information and everything else falls into place. And that's exactly what we do in these problems. So we need the equations to constrain our values. Once we have enough information, we can start getting some numbers, and those numbers lead to new numbers and other numbers, and eventually we've solved everything. Now, a word on signs here. The signs still have the same meaning that they did in all the other problems. The signs are related to our assumptions. If I had assumed, for example, in drawing my free body diagram that RAX was to the left instead of the right, I would have gotten a positive value here, and then I would have gotten a negative value here for B. So the signs you get depend on the assumptions you make. So be careful with that if you're comparing answers with your classmates or anything like that. You may have different answers up to the sign. You should have the same sizes, but you might have different answers up to that sign. The magnitude takes care of that, because remember, when you square a number, whether it's positive or negative, you get the same result. And I would encourage you, when you're finding your magnitudes here, don't even plug in negatives into the calculation. Understand that when you square a negative, you get the same result as if you squared the positive. So don't confuse yourself or your calculator by keying in that negative. It can only lead to bad things. If you forget to use parentheses or use parentheses in the wrong place, that negative can hang around instead of getting squared away. You have to get it right in your calculator, depending on the kind of calculator you have to wrap the negative in parentheses along with the number. I'd say just circumvent the whole issue by just plugging in positive numbers into your calculator. So to go to finish up here and fill in the magnitudes, I would just plug in 600 squared and then do 100 squared, add those together and take the square root. And to 5 significant figures, my magnitude here, which should always be positive. If you get a negative magnitude, you screwed something up. 0.29. So 608.29. And since B involves the exact same numbers, it's going to have the same magnitude, 608.29. And then we've got 100 squared plus 100 squared, added together, square root. That's 141.42. So that would be our final answer here, assuming there were no constraints on the sig figs. 608.29 for A and B, and 141.42. That is the total force acting on those joints. And if we were to go into a materials portion of the course, we'd then ask, well, could the pins being a certain diameter handle that force, or are they going to shear through? So we have a total force that we find. That's what we found here in the frame problem. So to review the process here, each pin contributes 2 unknowns to the problem. Our job in a frame problem is to find the magnitude of the reactions at each of the pins. And because we have more unknowns than we have equations in any one equilibrium problem, we're going to have to do several. The external problem is usually a good place to start. And then you break the truss up or break the frame up into the individual members. Many times you only have to work one more member to get the information you need. In other problems, you might have to do 2 or 3 members to get all the information you need. That's going to be the case in the next example. But any questions on this particular one? The equations may take a little getting used to. Getting just an equation and not a number is a little bit strange. It's a new thing for this type of problem, but the equations tend to be fairly simple because everything's at right angles. Everything's at 90 degrees since we've either got horizontal or vertical forces. So sines and cosines, we don't really have to deal with. So we get these nice, simple algebraic equations that we can just solve relatively simply. So let's try another example and see how this works on something a little more complex. So that was that example here. Here's another example. This is maybe a, looks kind of like a chair or something like that, that somebody's pushing on from behind. We've got a force here. And so we've got a roller support on the front. We've got a pin support on the back. And we've got 3 members. If we count up our unknowns here, we've got 2 unknowns at A. We've got 2 at B, 2 at C, and 2 at D. So there, 2, 4, 6, 8, plus 1 more at E, because E is a roller, it only has 1 unknown. So we've got a total of 9 unknowns here. When you count up your unknowns, you should always end up having a multiple of 3, because that tells you how many problems you're going to have to solve to figure out your pinned reactions. So here we're going to need 3 setups to solve this problem. Now, which 3 setups we do and what we set up is completely up to you. Any 3 free body diagrams will do it. Now, I usually like to go for the external problem, especially if I only have a pin and a roller, because I'm going to get numbers out of that. I have 2 reactions at A and 1 at E. If I treat everything else as internal, then by doing the external problem, I'll get 3 numbers. I'll get my reactions. But then I'm going to have to pick 2 members to work with. You could say, well, I'm just going to work with the members. I'll do a free body diagram for AB, for member AC. I'll do a free body diagram for member CE, and I'll do a free body diagram for member BD. That'd be 3 sets of 3 equations, which will get you a total of 9 unknowns. It's a different approach, but it'll get you the same answer in the end. And like I've been saying since the beginning, your answers can't depend on the method you use. The answers are the answers. The answers are what the stresses are, what the structure is experiencing. That can't depend on how we do the analysis, as long as we do it right. So any way you cut it, you should be getting the same answer. So I'm going to start with the external problem on this one, and then I'll share a little bit of my strategy for what I'm going to pick to work beyond that to get the other 6 equations I need. So let's draw up the free body diagram first here. There we go. So we've got 43.5 pounds, kind of a weird amount, but 43.5 pounds, 1 foot above A. And then we've got this thing up to C, looks like a total of 2 feet. But we've got that rail, BD, at 2/3 of a foot up, 0.667 feet. And then 1.333 feet up, we've got that. So let me label the joints: C, D, E, B, and A. All right, let's switch over to the page. There's the free body diagram. Now, these go to those points right there. We have a pinned supported A, so we have 2 unknown forces, and I'm going to assume them positive, RAX and RAY. We had a roller at E, so we just have REY. And our table is going to look pretty similar to what we had for the previous problem. We have some X's, Y's, and magnitudes, all in pounds in this case. But this time we have 5 points, A, B, C, D, and E. So we're going to have 5 rows in the table. A, B, C, D, and E. And another difference between this problem and the last one is that we have a roller at E, which means E is only going to have a Y direction reaction. There is no X direction reaction, so we can cross that one out. That's where we get our 9 unknowns. 1 there, and then 2, 3, 4, 5, 6, 7, 8, 9. So 2, 4, 6, 8 plus 1 more, 9. So 9 unknowns. So let's do our equations of equilibrium. So we have our sum of forces in the X direction. We have a positive RAX, and I'll draw my coordinate system here. We have a positive RAX. We have a positive 43.5 pounds. And we have nothing else. So nothing else in the X direction, so that gives us an equation. We can take our sum of forces in the Y direction. In the Y direction, we have a positive RAY. We have a positive REY. And nothing else. No other forces in the Y direction. So that equals 0. And then we have our sum of moments about a point. So let's stick with what works. We'll pick point A. Well, what forces are going to have moments? RAX and RAY are out. The 43.5 pound force is definitely going to have a moment, has a 1 foot arm. And REY is also going to have a moment. And I forgot to copy down the width here. That was 1.5 feet. So REY's arm is 1.5 feet. So our moment equation, we're going to have two terms, one from the 43.5 pounds and one from RUI. So sum of moments about A. We have 43.5 pounds at 1 feet. That's 43.5 foot-pounds clockwise, so it's negative. Then we have 1.5 times REY, pinned there, pushing up. That's counterclockwise, so positive. And that equals 0. So in this list, the only equation we can't solve right now is RAY plus REY equals 0. Well, we've got two other equations we can solve right away. RAX is negative 43.5. So that's a value that we've got and we can use and plug into our table. And I'd plug that in along with the negative. So negative 43.5. REY we can get from the moment equation. If we add 43.5 to both sides, we get 1.5 REY equals a positive 43.5. And dividing both sides by 1.5, we get 43.5 divided by 1.5. That gives us 29. So REY is 29. So we can fill that in over here. And we can now go to our y direction equation. REY is 29, and something plus 29 has to equal 0. The only thing we can add to a positive 29 to get 0 is a negative 29. So RAY equals negative 29. So we can fill that in on our table. Now, the reason I'm leaving these as negative is because when I do my next set of free body diagrams, I want to make sure that I don't get myself confused with negative signs and flipping directions and all of that. If you keep them the way you drew them for the supports, for the external supports, you won't get confused about what to do with them when you draw other free body diagrams. But at least with this external problem, we were able to get 3 unknowns. So 3 of our unknowns are down. We only have 6 left, B, C, and D. Well, we can't see what's going on with B, C, and D in the external problem because those are internal forces. They're inside the bubble that draws that determines where our system is. To expose the unknowns, we have to expand the frame. I like to think about it as blowing the frame up and looking at the individual pieces. Each of these 3 members, member AC, member BD, and member CE, those all have to be in equilibrium. So I can draw free body diagrams of each of those. So I think what I'm going to do here first is draw the free body diagram of each of those 3, and then I'll tell you which ones I'll do, which ones I'll figure out, I'll solve. So let's draw the free body diagrams down here. First, think of blowing the frame up. Look at an exploded view of the frame. Well, in an exploded view of the frame, I've got member A with this pin B over here, and then this other pin C up here, and that's way off in position. So I'm going to go down here again. Let's try that on a separate sheet. There we go. Missing my whiteboard. All right, so let's try that again here. So we have member A, C. So there's a pin at C. There's another pin right down here at B. And then we have something we've already made an assumption about. We've made an assumption about A. And so I'm going to carry those in because those are a support force. We've got RAX and RAY. Now, we've also got this 43.5 pound force here. And I'm going to leave off the geometry here for a moment. That's just one of the members. If I was drawing an exploded view, I'd have to have a horizontal member here, member BD. And then off to the side here, I'd have to have this slanted member, which has E at the end, REY. And then over here someplace, joint D. And over here someplace, joint C. So those are the three members of the truss, or members of the frame, just separated and split apart. And here's where we have to be careful. This only applies to the joints that are inside the member, inside the truss or frame. It does not apply to the reaction forces. When we draw the free body diagrams, we are exposing forces. There are forces acting at joint B, and I'm going to assume they're to the right, RBX, and up, RBY, excuse me. I'm going to do the same thing at C. Pin C is a pinned reaction. Pinned supports give us two unknowns, and I'm going to call them RCX and RCY. And since this is the first time I'm drawing arrows for B and for C, my technique here to keep myself from making mistakes with signs is to always assume positive the first time I draw that joint in a free body diagram. So here I've drawn members B and joints B and C exposed in this free body diagram. So I've assumed positive directions. The reason for that is the second time I see them, wherever I happen to see them in another member, I've got to take into account Newton's third law. Newton's third law says that for every action, there's an equal but opposite reaction. The force that member AC feels at joint B from member BD is going to be equal and opposite to the force that member BD feels at joint B from member AC. So when you draw these free body diagrams, you need them to be consistent with each other. You need them to fit together. And Newton's third law does that for us. So here, when I draw the free body diagram of member BD, because I've seen joint B before, I'm going to draw the forces in the opposite directions. So I'm going to draw them negative. I'm going to still label them with the same values, RBX and RBY, because they have the same values. They're just in opposite directions. Equal but opposite, Newton's third law. And you can kind of see this visually. It sort of looks like these two should fit together. It's sort of like fitting tabs into slots if you were putting some part together. They're equal but opposite, and they fit together. Now, to finish out the free body diagram of this horizontal member, I've never drawn D before. I haven't looked at the forces on D before, so that's the first time I'm seeing it. It's the first time I draw it positive. RDX and RDY. Now let's go over to member CE. There's the second time I'm seeing D. So I've got to draw the arrows so they'll fit with the first time I saw it. So Newton's second law says opposite directions. So I'll have RDY and RDX. Same thing here for joint C. I've seen joint C before. I've already made an assumption about the directions at joint C. So I've got to make the equal but opposite assumption the second time I see it. So this is probably the trickiest thing about doing frame problems. Oops. And keeping X and Y straight is apparently tricky tonight. But RCY, there we go. So the key idea is you've got to make sure these fit together. Now, it really doesn't matter whether you assume positive or negative first. All that matters is the second time you see it, you draw the arrows in the opposite directions. What this does, we saw in the last problem that from each free body diagram, we get equations. What this does is it makes sure that we're going to be able to use the same equations without causing sign problems. So if I get an equation out of BD that involves RBX and RDX, then the equations that I got out of AC that also involved RBX will be able to be used together. The answer that I get for RBX here can just be plugged right in here because I've already taken into account Newton's third law. So with that being said, let's discuss how I'd pick which members I'd have to use. I've got 3 possible free body diagrams here. So I've got 3 possible sets of 3 equations I can deal with. That's too many. I don't need 9 equations. I only need 6 because I only have 6 unknowns that I still need to get. So I only need 2 out of 3 of these. And the rule I follow with that is I always want to work with horizontal or vertical members. Horizontal and vertical members will always give you simpler equations to deal with, especially when it comes to the moment equation, because no matter what pivot point you pick, you're going to knock out stuff far away if you're dealing with horizontal or vertical. You're always going to be able to knock out, if you pick B as your pivot point, RDX is going to go away too, because it's got a line of action going through it. That doesn't happen on slanted members. If I pick E as my pivot point, I'm not only going to get RDX and RDY, I'm going to get RCX and RCY too. No matter what pivot point I pick, lots of moments are going to come in when you're dealing with a slanted member. So unless you absolutely have to, unless there's no other choice, avoid doing the free body diagram and solving the equations of slanted members. Go with horizontal and vertical members. They will give you the easiest sets of equations to work with. So that being said, let's do it. So let's take the one that looks simplest here is the horizontal member. So let's do that one here. If we do member BD, so member BD, we'll bring that off to the side here so we can clearly see it. We've got RBX and RBY. We've got RDX that way and RDY there. So there's our free body diagram. We'll separate that off there. So sum of forces in the x direction. We've got a negative RBX and a positive RDX. That equals 0. We do our sum of forces in the y direction. We've got a negative RBY and a positive RDY. That's equal to 0. And if we pick B as our pivot point and do our sum of moments about B, let's look at the forces that'll have moments. Well, RBX and RBY are out. So is RDX, since its line of action goes through B. But RDY will have an arm. We'll have a moment. So we're going to have to figure out what that arm is, or if we think about it a little bit, maybe we don't. We've got RDY times some arm here. Now, if we go back up to our original drawing, we could do some math and figure out what this length has to be. We know something about what the distances are, and we could figure out using the geometry what this distance is. But it turns out not to matter. It's always a good idea to look at that in your equations, kind of have a little bit of insight, look ahead, and don't just plug numbers in and try to solve the equations. You might save yourself a whole bunch of time. I could figure out what the length of this is so that we could figure out what our arm is going to be. But the thing to notice is only one force has a moment. And when there's only one force that has a moment, it's got to be 0. Because no matter what this arm is, there's nothing else for it to combine with. So that could be 3 feet, it could be 1.7 feet, it could be 0.67 feet. We could do the math and figure it out. but it doesn't matter what it is because the moment's got to be zero. There's no other force. If there was another force involved causing a moment, then we'd have to do some calculations. But in this case, there's no other moment involved. So our dy must be zero. So that gives us something that we can figure out, we can put into our table. Our dy is zero. So we can go up here to our moment, or to our table. Our dy is zero. Well, let's see if that helps us anywhere else. Well, in the y direction equation, if our dy is zero, our by has also got to be zero. So that's something else we can fill into the table. Our by is zero. Unfortunately, we don't get any information about rbx and rdx that could give us a number for either of those. But look at what happened in our free body diagram. We basically lost our dy and our by. This is a two-force member. The forces are along the line because member BD doesn't have any weird loads in the middle of it or anything like that. It's just connected at its ends. It looks just like a truss member. So it only has forces that are horizontal because it's horizontal. But we can't use this equation just yet. So we'll go and put that up into our equation bank. We've got negative rbx plus rdx equals zero. And if you think about what that equation says for a moment, it says rbx and rdx are equal. If you add rbx to both sides, you'll have rdx equals rbx, which is exactly what we have to have in a two-force member. In a two-force member, the forces at the ends are equal but opposite. So we got some information anyway. We got two numbers and an equation, which is about the best we can hope for when we've got four unknowns and three equations. So that was the member BD. And that knocked out two of my unknowns, but gave me an equation. I still have four unknowns left, but I've got one equation, so that counts against one of the unknowns. I'm going to get three more equations from my next setup, so that's going to give me everything I need. So let's take a look at the vertical member here and do the equations for the vertical member. Well, sum of forces in the x direction. We've got a positive RAX. We have a positive RBX. We've got a positive 43.5. And then we've got a positive RCX. Nothing else in the x direction, but that's already looking pretty ugly. Fortunately, we already know what RAX is. We can go to our table and say, well, RAX is negative 43.5. So we can plug that in here, negative 43.5, sign included. And that simplifies things for our x direction equation. The negative 43.5 and the positive cancel out. So our x direction equation just says RBX plus RCX equals 0. So our x direction came out not so bad. Let's do the sum of forces in the y direction. In the y direction, I've got a positive RAY. I've got a positive RBY. And I've got a positive RCY. But if we go back to our table and see what we can fill in, we just figured out our by is 0. So we can drop that out of the equation. And we just have RAY plus RCY equals 0. And now we have the moment equation. And for the moment equation, you have some choices about how to make this work out. And the same rule that we used with trusses applies here as well. You always want to pick as your pivot point where the most number of unknowns are. it wouldn't make a lot of sense to pick A here. You might be very comfortable with picking A here, but from an analysis point of view, picking A wouldn't make a lot of sense because we know RAX and RAY. They're just numbers. So eliminating them doesn't really help us solve the problem. In fact, if we picked A as our pivot point, although we'd lose RBY and RCY, we'd have moments from RCX and RBX, which we don't know. So we'd end up with another two equations, another equation and two unknowns, and we might end up getting stuck doing simultaneous equations. But if we pick pivot point B or C, either of those will make things a little simpler because they'll knock out something that we don't know. In fact, I'd probably go with C here because I know nothing about what's going on at C. I don't know RCY, I don't know RCX. If I pick C as my pivot point, then I'll get RBX, and I've already got a bunch of equations that deal with RBX. So that might be a good place to go. So let's do our pivot point at C. So we'll do our sum of moments about C. So let's see what we've got. We're going to have a moment from the 43.5, and we're going to have to figure out what the arm is for that. We won't have a moment from RBY. Doesn't matter anyway, it's 0. But we won't have a moment from that because its line of action goes through C. We will get a moment from RBX, since that's got some arm compared to C. And then at A, we won't have a moment from RAY because RAY shoots right through. We will get a moment from RAX. And to avoid problems with negatives, it's best to work these equations symbolically and then substitute in what you got from your equations or from your table. If you try to work in negatives here, you run the risk of flipping the arrow and then losing the negative or adding an extra negative in. Work it out using the symbols and the arrows and the assumptions you made, and then plug in the numbers from your table. You'll avoid making sign errors that way. So let's do our moments about C. So we're going to have 1, 2, 3 terms in our moment equation. So let's start at the bottom with RAX. We know what RAX is, but I'm going to put RAX in symbolically here. And if we look at our full scale drawing right up here, if we're at C, RAX is a total distance of 2 feet. 0.667 plus 1.333, it's 2 feet away. So the arm for RAX is 2 feet. And based on our assumptions, we've got RAX pushing to the right. That would be a counterclockwise moment, so it would be positive. So we have positive 2 times whatever the value of RAX is. Then we've got B. We've got RBX according to our drawing. So we're going to have RBX times some arm. The arm for RBX, if we look at the distance here, that's 1.333 feet. So we have 1.333 RBX pinned at C, pushing to the right at B. That would be a counterclockwise moment, so also positive. And then we've got the 43.5 pounds. According to our drawing, if it's 1 foot from A to the 43.5 pounds, and it's 2 feet from A to C, then it must also be 1 foot from C down to that 43.5 pounds. So it's just 1 foot. So we have 1 foot times 43.5 pounds, pinned at C, pushing to the right, counterclockwise moment, so positive. So those are our 3 forces, our 3 moments. Now we can see from our table what we can use. Table says RAX is negative 43.5. So plug that in. You've got 2 times negative 43.5 plus 1.333 RBX plus 43.5 equals 0. So 2 times 43.5, that's looks like negative 87. Plus 1.333 RBX plus 43.5. And if we go through and solve this, if we combine the two numbers together, negative 87 and positive 43.5 is a negative 43.5. So we get 1.333 RBX minus 43.5 equals 0. Add 43.5 to both sides, so we get 1.333 RBX equals 43.5, and divide both sides by 1.333. And we get 32.633. So RBX is 32.633, and this is pounds. So RBX comes out a little bit strange, but not too bad. We could solve for that. So we've got a number we can plug into the table now. RBX is 32.633. Now we can look back at our equations, both what we've got here and what we've got in our equation bank, and we can figure out if there's any simplification. Well, it doesn't help us here with RAY and RCY, but knowing what RBX is gives us what RCX is. So if RBX is 32.633, and we have to add something to that to get 0, then RCX must be negative 32.633. So we can go back to our table. RCX is negative 32.633. And knowing what RBX is, we can go back to our equation bank, and that says negative RBX plus RDX equals 0. So negative 32.633 plus RDX equals 0. So RDX must be a positive 32.633. And then the last thing we can do, well, we know what RAY is. RAY is already in our table. RAY is negative 29. So we'd plug in negative 29. So we have negative 29 plus RCY equals 0. So RCY must equal a positive 29. So usually in these problems, you see a lot of repetition of the same values. So there we've got everything filled in. We've used all 9 equations that we made up. One set of 3 from the external problem, where we got 3 numbers, our values at A and E. Then we did the free body diagram of the horizontal, which gave us 2 numbers, the 2 zeros, and an equation that we could use later. And then we did the free body diagram of the vertical member and found our values for our BX, and the value for our BX led us to our CX, and knowing our BX also got us our DX. So everything fell apart at that point. So we've got all our values. The only thing left to do is find our magnitudes. So again, ignore the negatives when you do your magnitudes. They'll just cause you problems if you try to key it all into your calculator. Just square the positives, square the values independent of sign, add them, take the square root, and you'll get your magnitudes. So 43.5 squared plus 29 squared. Here we get 52.280. If you've only got 0 for one of the values and you've got some number for the other, that is the magnitude. Because when you square this, add nothing to it, and then take the square root, you get back to where you started. So we have 32.633. Just lose the negative sign. Magnitudes are always positive. So 32.63. Oops, not that one. Sorry. this one, 32.633. Here we've got 32.633 squared plus 29 squared, square root. There, that's 43.657. So 43.657. And then this one's just going to be 29 because there is no value for the x direction. So there we go. There we've got our magnitudes. Magnitudes should always come out positive, and they should always be bigger than the values that you put in here. One of the signs that you had some issues keying signs in is if you got a smaller value over here. Magnitudes always have to be bigger than the length of the hypotenuse of a right triangle. So that one's a little more complex of an example, but it can be worked the same way as the previous example. So if you're skilled at using free body diagrams, if you are able to handle the non-concurrent force problem, you're most of the way to being able to solve these problems. The only little quirk that we have to be aware of is that Newton's third law issue in dealing with the free body diagrams. You got to make sure you've got consistent information between free body diagrams. The only values that stay the same as your original assumptions are those external supports. But you do this flip-flop thing on the internal joints, on the joints that are joining members together, not members and supports. Any questions on that problem?
Nope.
All right, well, let's take a break. We'll take about a 10-minute break here. I'll put a problem up for you to work on and get a little bit of feedback on solving frame problems. So we'll pause. We'll be back in a few minutes. All right, so here's our practicum problem for the evening. We've got a wall-mounted structure. And you might want to say at first this is a truss problem, but what makes this a frame instead of a truss is this point right here. If this was a truss, then this would have to be two separate members horizontally, where we'd have member BD and member BC. And that wouldn't work in this structure because these are all pins. If we applied a load here, that would just swing down. These are only two pieces of material, and now there's a force at that joint B between members CD and member AB that wouldn't be there wouldn't be allowed in a truss. So this is a frame problem. So let's see how to work this out. Well, let's come up with a strategy here first. We've got 6 unknowns. They want us to find the reactions at A, B, and D. So there's A, that's a pinned support, so 2 unknowns there. B is a pin, so that's two unknowns, and D is a pin, so another 2 unknowns. So we've got a total of 6 unknowns. And like I said, it's always going to be a multiple of 3. So we have to do 2 setups at a minimum here to get our values. Since I've only got 3 possible problems I can solve here, I've got the external problem. I could analyze the horizontal member and its free body diagram, and I can analyze the slanted member. But if you follow my advice from earlier this evening, don't deal with slanted members unless you have to. So my strategy here is going to be to do the external problem and then to analyze the horizontal member. That'll give us something that that'll be 6 equations total. We'll get some numbers along the way, and we'll be able to solve everything. So let's do the free body diagram first, and I'll switch to a sort of a line drawing for that instead of the thicker pieces I've drawn here. So we've got a slanted member, we've got this horizontal member. We've got 5 kips of force down there. We've got reactions at A, and since it's a pinned support, I'm going to call that RAX and RAY. We've also got a pinned support down here at D. So I'll call that RDX and RDY. And we've got some geometry, and I screwed up the scale here, but this was 4 feet. This is also 4 feet. And this is just 2 feet. So I went a little far on that drawing. So that's the external problems free body diagram. If we do our sum of forces in the x direction, so sum of forces in the x direction, we've got positive RAX and a positive RDX, and nothing else in the x direction. If we do our sum of forces in the y direction, we've got a positive RAY, we've got a positive RDY, and a negative 5. And then we have to pick a pivot point and do our moments about that pivot point. I'm going to pick D on this one for no particular reason. A would have worked just as well. But sum of moments about D, we get, well, if we're picking D, we're going to lose RDX and RDY. We're also going to lose RAY since the line of action of RAY goes right through D. But RAX will have a moment, and so will the 5 kip force. So 2 terms in our moment equation. The arm for the 5 kip force is 6 feet. So we have 6 times 5, 30. And that would be a clockwise moment, so it's negative. And then we've got the arm for RAX is 4 feet. That would also give us a clockwise based on the assumption that we've drawn here. So that's negative 4 RAX. And that equals 0. Well, we can solve the moment equation if we add 30 to both sides. If we add 30 to both sides, we get negative 4 RAX equals a positive 30. Divide both sides by negative 4, and RAX equals a negative 7.5, and that's kips. So we've got a value we can plug in into our table. And we did over here in red, RAX was negative 7.5. Now, that it's negative still means the same thing here for the external problem. It means that it's opposite what we assumed. And that kind of makes sense physically. We would expect if we're pulling down over here that this top portion is going to try to come away from the wall. So it makes sense that the reaction at that support should be in the opposite direction, should be toward the wall to hold this thing. If you had to reach out and grab onto that, you'd be pulling toward the wall, not away from it, to try to keep this thing in equilibrium. So we get a negative, but again, negatives are really tricky in these frame problems. So we've really got to be careful about our assumptions and sticking to them and tracking those negatives through, or we're going to get all confused. So it's good to be able to see the interpretation, but I wouldn't do anything mathematically with that. I'd just leave it as a negative. Well, now that I know what RAX is, I can go to my x direction equation and plug that in. I've got negative 7.5 plus RDX equals 0. So solving that's relatively easy. RDX is a positive 7.5 kips. And for a similar reason, we can kind of explain the reaction force there. If you're pulling down out here, it may be trying to pull away from the wall up here, but it's trying to wedge this end of the member into the wall. So whatever's holding on to it needs to push out of the wall to support it. So RDX was a positive 7.5, and we put that in the table up there. RDX was a positive 7.5. And then we have our y direction equation, and unfortunately we don't have enough information to solve the y direction equation. We have RAY plus RDY equals 5. That's the best we can really do. If we clean that up a little bit, add 5 to both sides, we've got RDAY plus RDY equals 5. So we can't use that equation just yet, which is about what we could expect if we knew we went into this with 4 unknowns and only 3 equations. We got the best possible scenario. We've got 2 numbers and 1 equation. So that one we'll have to store for later. So I'm going to just box it in here rather than copying it over to the front page so that I can see it a little more easily when I come back to it. So that's all we can get out of the external problem. 2 numbers and this 1 equation. To go any further, we need a new free body diagram. And I'm going to work on the horizontal member. And the free body diagram for the horizontal member, we've got part of it already here. Remember, we leave the reactions the same at the supports. The only thing we have to deal with special is this interaction at B. But since we're only going to analyze one of these members, we're not going to analyze the slanted member. We don't really have to draw the free body diagram of the centered of the slanted member or deal with Newton's third law at that joint. So I'm only going to need one setup for this horizontal member. So going over to another scrap page here, the horizontal member is going to look something like this. It's got its 5 kip force there. We've got B, and since I've never seen B before, I haven't used B in any free body diagrams before, I'm going to assume positive RBX and RBY. And then at D, I've already made assumptions about D, so I'm going to keep those because D is not a Newton's third law situation. I'm not going to look at 2 different free body diagrams that look at D differently. B, you've got 2 free body diagrams that look at B differently. B on one member is equal and opposite B on the other, but D only ever shows up on one member, that horizontal member. So D isn't going to change. I've got RDX and RDY. And this was 4 feet and 2 feet. So let's do our equations of equilibrium for that one. Sum of forces in the x direction, we've got RDX plus RBX equals 0. In the y direction, we've got RDY plus RBY minus 5 equals 0. And sum of moments, we'll have to pick a pivot point, and I'll just go ahead and pick D again for that. That'll knock out RDX and RDY. It'll also knock out RBX, since the arm for the line of action for RBX goes right through the pivot point. RBY will have a moment, has an arm of 4 feet, and the 5 kips has a moment, an arm of 6 feet. So we'll have 4 RBY positive because it would give us a counterclockwise moment. And then we'll have a negative 30. 6 feet times 5, clockwise moment, so it's negative. Well, those equations we can work with. We can solve RBY directly. Add 30 to both sides, divide by 4. RBY comes out to be a positive 7.5 kips. And we can put that into our table. RBY is a positive 7.5 kips. And let's see, RBY we can use in the y direction equation. If that's 7.5, then we have RDY. 7.5 minus 5 is a positive 2.5, and that equals 0. So RDY is a negative 2.5 kips. And we can fill that in. RDY is negative 2.5. And then for RDX and RBX, we didn't get anything from these two, but we already had something filled in the table. We had RBX from the previous set of equations. We had figured out that RBX, didn't we? Or we had RD, yeah, we had RDX, excuse me. We had RDX was 7.5 kips. So now we can go and use that in our equation here. R dx plus R bx is 0. So if R dx was 7.5 plus R bx is 0, R bx must be negative 7.5. Kips. And so we can fill that in our table. And R bx is negative 7.5. Then the last thing that we have to do is use this equation, the RAY plus RDY. Well, we figured out here, RDY is negative 2.5 kips. So we figured out over here, RDY was negative 2.5. So we can plug in negative 2.5 there, add that to both sides, and RAY comes out to be a positive 7.5. That gets us all 6 of our unknowns. Now, something to notice here with our numbers, before we go and find the magnitudes, which are just the square roots of these squared, the sum squared. So if you look at what's going on at B and A, they're the same values in both directions. That means we've got in A, for example, we've got negative 7.5. So we've got 7.5 to the left, and we've got 7.5 up. That's going to be at a 45-degree angle. It's showing us that member AB has a force aligned with it. It's at a 45-degree angle. So is this. This has to be at a 45-degree angle because it's 4 feet by 4 feet. Member AB looks just like a truss member because it only has forces at its endpoints. Now, B kind of shows the same deal. You got a 45-degree angle there. So we get, whenever we've got a two-force member, whenever we've got a regular truss member in a frame, the forces will end up looking the same on both ends. We'll have the same X and Y components because they have to line up with the member. And when you find the magnitudes, you'll find the magnitudes for those will be the same. So a clue that you've got a two-force member in a frame is that you get the same reaction force at both ends. In magnitude, anyway. D, we can see what's going on with D, and it's negative 2.5 here, because if you think of this as kind of a lever, if we're pulling down here at C, further away on the opposite side of this pivot point, this is going to try to go up. So D has to be holding it down. D has to be pushing down to keep this horizontal. And it has to be pushing down with half the force because it's farther away. Think about levers and mechanical advantage and all that. You've got 5 kips at 2 feet. That's the same as 2.5 kips at 4 feet. So the directions kind of make sense there. So those are our magnitudes at A, B, and D. And then we rounded those to 3 sig figs. So it might take a few more problems until you're feeling comfortable with this, and I'll give you the same advice that I gave you last week. There are some sample problems already worked out. If you go and look at last year's videos, the videos from spring 2020, those are still on the YouTube channel, and you can find I think it's even corresponding lecture numbers. So you can find the one for this lecture, and you can find, well, you'll see the same problems worked out in the lecture portion because I didn't change the lecture notes, but the practicum problem, I might have picked a different practicum problem to work on. So you might find something else worked out there, and you can see things in a slightly different way if you need a little bit more practice on those. But essentially, it all just comes down to being able to handle 3 equations and 3 unknowns and drawing different free body diagrams. Any questions on that one?
Nope.
All right. Then let's see here. Let's go back to the notes for just a second. So next time, we're going to practice on primarily frames, but I'm likely to end up working out a truss problem since there's probably going to be questions on the homework. So next time we'll do that. Monday next week will be just all practice, no new content. Monday next week. We will have a quiz Monday next week, but that'll be on method of sections, and then exam on Wednesday. If there are no other questions, have a good night. I will see you on Wednesday.
Take it easy.
Thank you.